Good morning, everyone. So today we're going to talk about power factor correction. We're continuing this chapter that's about power and AC analysis. And we want to now touch on a topic called power factor correction. Right? What are we correcting? What's the idea here? So the idea is that we said that one particularly useful way of describing loads that present to any source. So you have any source, right? This source, AC source, you can add a load to it so that you can draw current from the source. And that source, I mean, it could be a generator that's running, bunch of generators from the power plant. However you build the source, right? It presents itself in circuit theory as just this simple voltage source, right? It could be more complicated. It could have like an input impedance and all of that, right? But the most simplest way you can look at a source is just as a voltage source, right? And the source drives a load, and a particularly useful way of describing AC loads are by their power requirement. How much power do we need to supply this load? For example, if you buy a light bulb, right? They don't tell you on the nameplate, oh, this is a 50 amp bulb or a 1 amp bulb or a half an amp bulb, right? They could say that, but it's more useful for them to describe the bulb in terms of the power that it draws. So they say it's a 120 watt bulb or a 60 watt bulb, because that's ultimately what a load is. It's an element that derives power from the grid, right? So most loads are described by power, what power they consumed, and then by their power factor, right? And it is mostly lagging. Power factor sometimes could be leading, but mostly could be lagging, right? Mostly will be lagging. Right? And then we know that the apparent power, which is the magnitude of the complex power times the power factor equals the average power. Right? And this follows from the previous formulas that we derived, right? Apparent power is just Vrms, Irms. Power factor is just cosine theta L, where theta L is theta V minus theta I. Okay? The theta is what's called the power factor angle. Right? And we derived all those equations in previous lectures. So using this, I can say that the apparent power is just the average power over the power factor. Okay. This is the idea, and sources of power, typically like your utility or any entity that provides power, does not like a power factor that's lagging too much. Why? Well, let's say we have the load, right? What does it mean for, like, let's say you're drawing 100 kilowatts. And let's say the power factor is bad. The power factor is 0.5. Horrible, right? What does that mean? That means your apparent power is going to be what? It's going to be the power you're drawing over the power factor. So your apparent power actually will be much larger than the power that your load is consuming. Your apparent power is going to be 100 kilowatts over 0.5 is going to be right, it's going to be over half, so it's going to be times 2 times 2, it's going to be 200 kVA. Okay? So that means although you are consuming only 100 kilowatts, you are consuming 200 kVA apparent power. Why is that important? Well, if the source is right next to your supply and there's limited impedance in between, that's not important. But if your source is like a utility that's far away, and then you have a transmission line in between, so this is a transmission line. So typically this will be like a resistor, an inductor, right? So if you have a transmission line in between, what does higher apparent power mean? Well, higher apparent power means higher current, right? Because apparent power is VRMS magnitude IRMS, right? So the voltage is the same at the load. The voltage is that 120 volts or 220 volts or 240 volts, whatever the utility is providing. But the apparent power is larger. That means the current is larger. That means through the transmission network, a larger current needs to flow, right? To provide the same amount of real power at the load, right? So 200 kVA, a current that's equivalent to 200 kVA apparent power needs to flow through the transmission line to provide me 100 kilowatts at the load. And we know that when we have higher current flowing through the transmission line, that's higher losses through the transmission line, higher losses over the system, the whole transmission system overall. So the utility has to invest money in reducing the resistance of the transmission line or the impedance of the transmission line. So they have to make the conductors bigger and wide and heavier with a larger cross-sectional area and so on and so forth. So they have to add in more expense, right? While if the power factor is improved, is 0.9, for example, or close to 1, the kVA goes down, the IRMS goes down, the losses in the transmission line go down. So it's always in the interests of the provider of power for the power factor of the load to be as close to unity as possible. Could the power factor be leading? That's very rare. Most power factors are lagging because most what are the most industrial loads? Most industrial loads are consistent of machines, of motors. And motors are essentially big inductors, right? The stator of the motor is a big winding of wire, which is an inductor. So that's why most loads are high loads are inductive. Okay, so this is the problem. Power factor could be bad for some loads. How can we correct for it? Well, we touched upon this in a previous lecture, I think. The way to correct for it is to take our load and then connect in series with it, in parallel with it, a bunch of capacitor banks, right? So adding capacitors in parallel to the load is the way to correct for the power factor, right? So let's look at it. Let's look at it formally. Okay, so we have the source, whatever it is, and then I have my load. My load is consuming some PL power, and it's consuming some reactive power, right? And then if I go to the complex plane, so this is S load, let's call it S old. So this is the complex power before correction, before we try to correct the power factor. So SL or S old is just PL plus J QL, right? So I can draw it like this. This is PL and this is QL, the reactive power consumed by the load, and then the real power consumed by the load, right? And we said this angle is the power factor angle. This is theta old, let's call it. This is theta VL minus theta IL. Yeah, we established that from the formula for S. S equals VL IL conjugate. That's going to be VL. This is those are phasors. This is going to be VL RMS magnitude. Assume this is in RMS, and then IL magnitude RMS, and then this is going to be theta V minus theta I. Right. So the power factor angle is theta V minus theta I. The power factor is the cosine of this angle. Right. The power factor is the cosine of theta old. Right, because that gives me the real power. The real power is going to be VL RMS IL RMS cosine the power angle, theta V minus theta I. All right. So this, I mean, our power angle is going to be this, and our power factor is going to be this. And let's say the power factor is bad. This is much less than unity, less than 1. Let's say it's 0.7 or something. Right? How can we improve it? Just looking at the geometry of it. So I want. How do I improve the power factor? Right. So I want to improve the power factor, increase the power factor. What does that mean? That means I need to. I want to reduce the theta of the load, right? Because the smaller the angle, so this is cosine, right? The smaller the angle gets, the closer to unity I get, right? This is theta. This is cosine. Right, so I want to reduce the angle. How do I reduce the angle from this graph? Right? So one way, there are two ways. We can either increase P. We can let's say we have a factory and I want to improve the power factor. Well, what I can do is I can draw in more power. I could increase my real power, right? I want to increase my real power without increasing my reactive power, right? So I could have a factory, and then one way I could do it, if I have my factory and it has a bad power factor, I can increase my real power without increasing my reactive power. One way I could do it is I can get a bunch of resistors and load the utility or the grid with a bunch of resistive loads. Resistive loads are not reactive, are purely real, right? I mean, but that's a very wasteful way. I mean, I'm improving my power factor, that's correct, but I'm wasting a lot of energy burning it in the resistors. So I could put in a bunch of resistors here, right? And this will increase the power going into the load. It will be the power going into my machinery plus those resistors, and that will improve my power factor, but it's a very wasteful thing to do. Why? Because, I mean, resistors consume power. So it consumes energy. They're going to heat up and they're going to waste a lot of energy, right? So it's more economical to improve the power factor by changing Q. And how do I do that? I need to. So the other way of doing that is to take Q load and decrease it. If I decrease Q load, I will naturally get a smaller theta, and getting a smaller theta is going to improve my power factor. The question is, how do you reduce Q load? The answer is by inserting a capacitor. Right? So the capacitor, so my load consumes positive VARs, right? Because it's inductive, but my capacitor. My load sources negative VARs because it's inductive, but my capacitor sources, my load, because it's inductive, sources positive VARs. My capacitor, because by its very nature, because it's lagging, because it's leading, sources negative VARs. So they cancel out each other. So I'll show that in a okay, so that's what we want to do. Let's derive that. Okay, so we want to reduce the overall QL by connecting a capacitor in parallel. So again, I have my source, right? And just before, this is my transmission line, just before my load, I'm going to add a cap. The factory is going to have a bunch of capacitor banks connected in front, and this is the original load. Lagging, PF lagging, right? And this is the factory. Let's see, factory or industrial customer or whatever, right? So this cap, the total power going into the factory is going to be going to the factory is going to be the current going into the load plus the current going into the cap, right? And this cap is gonna reduce the power factor. So what's happening here? So let's go back to S old before we added the capacitor, right? So this is P old. P old doesn't change. We do not want to change the power. This is theta old, which is theta VL minus theta IL. This is IL here. And this is Q old. This is the reactive power consumed by the customer, by this load. Right? When I add, so we said the inductor consumes or absorbs positive reactive power. The capacitor we established consumes or absorbs negative reactive power. So the reactive power is not going to be consisting of two components right now. It's going to be Q old plus Q cap, and the Q cap will be negative and in the opposite direction. So if I sum up those two complex numbers, I end up with this smaller triangle. So I end up with Q new here, which is just Q old minus Q cap, and then the same P old. So I kept P the same and I reduced Q, and this is S new. So I end up with a smaller power angle. So this is theta VL minus theta IT, this current. So now I end up with a smaller power angle. Okay? So this is VL. Okay, so I end up with a smaller power angle. What's Q cap? I mean, we can quickly calculate Q cap. We know that S cap equals VL times IC conjugate. Always fall back to this formula. But we know that VL is just going to be just the magnitude of VL RMS. Right, and then using Ohm's law, I can write VC IC as the same voltage, VL phasor. Oh, sorry, I kind of jumped the gun a bit. So this is still VL phasor. So I see the current going through the capacitor as a phasor. Using Ohm's law is just V on the line divided by the impedance, right? Ohm's law. What's the impedance? 1 over j omega c, right? So it's going to be j omega c conjugate. So I'm going to end up with VL phasor conjugate. Conjugate of j is going to be minus j omega c. So S cap is going to be VL times VL conjugate is just going to be the magnitude squared, right? And this is RMS, of course. When I write S this way, everything here is RMS. Okay, the S formula presupposes that everything is expressed in RMS, right? And this is going to be minus j omega c VL RMS squared. So, of course, S cap is just P plus J Q cap, right? And of course, P cap is 0. There's no real power consumed by the capacitor. So Q cap is omega C VL RMS squared. That's a quick way to calculate this. Okay, you can always fall back to this formula. Right. So let's rederive it this way. Okay. So I want to relate it to S new and S old. So what's S new? I can use conservation of power to notice that S old is going to remain the same, right? That won't change, right? Because the voltage is the same applied to the load. I just added a capacitor that gave me some extra S, right? That's summed up with the old S. So S new really is equal S old, the same old S, plus the extra S that I added into the circuit, which is the S cap. So that tells me that S cap needs always to be S new minus S old. But S new is P old plus J Q new, and S old is minus P old minus J Q old. This cancels with this because P is not changing, so I end up with J Q new minus Q old. which is what? This is Q cap, right? The only thing that makes Q new bigger than Q old is the capacitor, existence of the capacitor, which is providing the difference between the old and the new reactive power. So we can say S cap equals J Q cap, right? And as we derived previously, right, we did this derivation here. Q cap is this. Sorry, minus. I forgot the minus here. So there's a minus here. Okay, right? So Q cap is just minus omega C V RMS squared. So this is going to be minus J omega C V RMS squared. So this is S cap. Okay. And like I said, what's the whole goal of this? The goal of this is to reduce this angle. By doing this, by getting adding the capacitor and going from Q old to Q new, we reduce the angle, and reducing the angle allows us to increase, right? So theta VL minus theta IT goes down. That leads to PF going up, and that's what we want. We want the power factor to improve. Okay, let's do an example. This is, I think, clearer when we go and do a bunch of examples. So let's do some examples from the textbook. So we have a facility we have a facility operating at 277 volt RMS, 500 kilowatts real power at a power factor of 0.75 lagging. So this is not a very good power factor. It's typically you want a power factor of 0.9 or higher. Okay, so and this is a particular example of how utilities could charge power to customers. So they could, they could charge power to customers based on two criteria. So there's something called the energy charge, which is the classical base way of charging power. It's just they install a meter at the facility or your house, and they measure the energy that you consume, and then based on how much energy you consume, you pay a certain set amount. So you could have, for example, in this example, the charge could be 2 cents, is 2 cents per kilowatt hour. Kilowatt hour is a unit of energy, by the way. So you're used to energy being what? Energy can be measured in joules, right? But energy is also power times time, right? That's what energy is. So energy also has units of watts times the units of time. If you set the time to be 1 hour, you can represent energy in units of watts hour. So this is called watt hour, or abbreviated as WH. Right? So it's a measure of energy. It's a measure of like 1 watt hour is the energy that you consume if you keep a 1 watt source turned on, or a 1 watt load turned on for 1 whole hour. Across this hour, it will keep consuming power. It will keep consuming the 1 watt, and the total amount of energy consumed in 1 hour is represented by a unit of energy called the watt hour. Of course, kilo is 1,000 watt hours. So this is just an alternate unit of energy that's very commonly used in power systems. Okay, so that's the base charge. But then there's something called the demand charge. right? And this is an extra kind of charge that depends on your power factor. So the demand charge is as follows in this example. So the demand charge is $3.5 per kilowatt per month, only if the power factor is good. If the power factor is larger than 0.9, less than 1. Okay. So if the power factor is good, hey, you pay the demand charge based on your real power consumption. If your power factor is bad, then we're going to have you pay $5 per kVA. So if the power factor is bad, now you're going to pay based on your apparent power, not your real power. Right? Because the apparent power is still something that is expensive to the utility. Higher apparent power means higher currents that have to flow through the transmission line, meaning higher losses. The utility might have to upgrade the transmission lines and so on and so forth. Right? You might exceed the current capacity of the transmission lines. Right? So if your power factor is bad, this is the demand charge that you pay. It's $5 per kVA per month, and this is if your power factor is less than 0.9. Okay. So how much this kind of utility where they have this sort of lagging power factor, how much would they be paying in total monthly charges? So the monthly charge is as follows. So it has the monthly energy charge. So that's simple. They're consuming 500 kilowatt. That's their power, but that's the power. We want to get kilowatt hour from that power, right? So we multiply that by 24 hours. There's 24 hours a day, assuming they are running, 24/7, and there are 30 days a month. So this is, let me rewrite this. So this is 500 kilowatt power times how much they are running. So energy is always power times time. So this is 24 hours per day. I'm going to write all the units times 30 days. So day cancels with day, and I end up with kilowatt hours. So if I do the math, of course, this is times $0.02 per kilowatt hour. Right? And this kilowatt hour cancels with this hour and this kilowatt. So if I do the math, I do 500 times 24 times 30 times 0.02, I end up with $7,200. Okay, what is the demand charge? Now the demand charge will depend on well, because the power factor is less than 0.9, the demand charge will depend on the kVA. So we need to calculate the kVA. We need to calculate the apparent power. Let's call that S old. We know that the magnitude of S old is going to be the apparent power. What's the magnitude of S old? It's the real power over the power factor. Again, remember, apparent power equals apparent power times power factor equals real power. So the magnitude of the complex power, or which is the apparent power, is just the real power over the power factor. So this is 0.75. And what is the angle? The angle is just the power factor angle, right? Which is cosine inverse 0.75. Right? And then we can calculate this. This ends up being 666.67, and the cosine inverse of this is 41.41 degrees. Of course, this could be positive or negative, right? Remember, because both a positive angle and a negative angle will give me the same cosine, but because the power factor is lagging, the angle between the current will be behind the voltage, so this angle will be positive. So this is kVA. right? So this is the apparent power. The magnitude of the complex power is the apparent power. So the demand charge in this case that they have to pay because of their bad power factor is going to be $5. What did we say? Per VA, per kVA, right? That's what it is, right? $5 per kVA times 666.67 kVA, right? So it's going to be 5 times 666.67 is going to be $3,333.35. Right? So the total charge is going to be 3,000 plus 7,000 something, which is going to equal $10,533.35. Okay, so let's say they fix that. So this is their total charge. They're paying a penalty to the utility due to their bad power factor. So they want to fix this and they want to install a capacitor in front of their factory or their facility. And they want to raise the power factor to 0.9. Let's say they install the capacitors and they successfully do that. They're able to do that. What's the S new in this case? So we want to calculate their new kVA so that we calculate, well, now that they increase the power factor to 0.9, their demand charge will be based on kilowatts again, right? But let's calculate their S new. Their S new is going to be, again, it's going to be the new apparent power, which is 500 kilowatts. Now by adding the caps, let's say they raise the power factor to 0.9. So now the power factor is 0.9. So this is their new apparent power. And their new angle now is going to be cosine inverse 0.9. So this is equal to 555.6, and the angle now is 25.84 degrees kVA. Okay, so the new demand charge now, now they succeeded in raising their power factor to 0.9. So now we use this rate, 3.5. So the rate is now 3.5 dollars per kilowatt times 500 kilowatts. We end up with 500 times 3.5, which is $1,750. So now the total charge is going to be $8,950. Okay. So the statement here is they just added the caps and they raised the power factor. The question is, you need to ask yourself, how much caps do they have to add to achieve this? So the assumption here is that they achieved this. And we calculated S new from S old, assuming they achieved this. What kind of capacitors do they need? What kind of capacitors do they need to achieve this feat? Right, so the way to calculate the amount of capacitors is as follows. So we know that the S new equals S old plus S cap. So S cap equals S new minus S old. But we already know what S new is and what S old is, right? S new is 555.6 with an angle of 25.84 degrees minus S old is up here, 666.67. So it's 666.67, 41.41 degrees kVA. Okay, and then we want to do this calculation. We have to turn this from polar to real. So we end up with, if I do this, I take 555.6 cosine 25.84 minus 666.67 cosine 41.4 degrees. I do the math, I end up with this small number, right? I should get 0 here, because remember, this is the capacitor I'm talking about. So the S cap the real part of S cap should be 0. But I get a very small value here because of rounding errors. Right? If I take more significant digits here, I would get a smaller number here, closer to 0. So I can just ignore this. This is due to rounding errors. What's important is the imaginary part, which is going to be minus J 198.8 kVars. Right? So that means that Q cap is minus 198.8 kVars. And we use kVars instead of kVA because this is just the imaginary part, which is the reactive part. Okay? So we derived Q cap in this lecture. We said Q cap is omega C VRMS squared equals minus 198.8 kVars. And we just have to do the math now. So C is 198.8 times 1000 over omega, which is 2 pi 60. The frequency of the line is 60 hertz. And then VRMS squared, which is 277 squared. So if we do this calculation, we end up with the capacitor that is needed to improve the power factor from 0.75 to 0.9 being 6.87 millifarads. Now the problem in the textbook goes through a side exercise where they talk about the cost of adding the caps. So yeah, if you add the caps, you're gonna improve the power factor and reduce your energy bill, but the caps themselves are costly. So you're gonna pay money to install the caps, and they have a limited lifetime. But still, it's gonna be, if you do the cost-benefit analysis, it's still gonna be beneficial because this demand charge you're paying every month, while the cap is a one-time installation cost. So I think they did the calculation and they found out that with a certain cost of capacitors, if you use a certain cost, it turns out you can pay off the caps by reduced demand charge in 12 months. And after 12 months, you're free. You don't have, I mean, the caps are the caps pay for themselves within 12 months. Okay? That's why it's very economically attractive for institutions to install caps and improve their power factor. Okay. Let's do the other example. Okay, so another example, just so that this sticks with us. Right. So the other example is we have a industrial motor load. Right. The example is of some facility that has industrial motors that are used to build kayaks. That's the example. Right. So, I mean, the particulars of the load are not important. What's important from a power analysis perspective is how much power the load consumes. So the load consumes 50 kilowatts at power factor 0.8 lagging, right, from a 220 volt RMS supply, which is a 60 hertz line. So this industrial motor that's used to build kayaks is it's a load, and it's like we said, 50 kilowatts, 0.8 lagging, and the line voltage V line is 220 0 degrees volt RMS, of course. Again, it's more conventional to give RMS values. Okay, and this is a 60 hertz line. Right. So you want to raise now the power factor to 0.95 lagging, again by capacitors. That's the best and cheapest way to do power factor correction. Capacitors are reliable, cheap, relatively. I mean, they just sit there. They're passive elements. There are ways to do what's called active power correction, active power correction, power factor correction, where you have to have a device that has switches in it that's continuously switching, right? So that's a more complicated affair, and that's more expensive and less reliable because the switches could fail, right? capacitors are the most straightforward method of what I'm trying to say is that capacitors are the most straightforward method of doing power factor correction, but they're not the only method for doing power factor correction. Okay. So yeah, I mean, by now you should know that the steps. So when I raise the power factor, what's S old? S old, that the old power factor is, well, the old apparent power is the magnitude of S old, which is 50 kilowatts over 0.8. We just take the real power over the power factor, and then the power factor angle is cosine inverse 0.8, and that gives me 62.5, 36.87 degrees. I'm taking more significant digits here so that I get more accurate results, kVA. And then S nu is just going to be the S due to the improved power factor. So now I divide by 0.95 and I take the power factor angle to be cosine inverse 0.95, and the S nu is 52.63, 18.19 degrees kVA. And I'm taking two significant digits to improve the accuracy. So now S cap is just S nu minus S old. So this is going to be 52.63, 18.19 degrees minus 62.5, 36.87 degrees kVA. This, right? And then I do my conversion from polar to rectangular. And I sum those two complex numbers. When I do that, I get like a very small number, 0.000 something. So it's zero pretty much. Right? So I get 0 here on the real part, and then minus J 21.07 kVARs. Right? I know that S cap is just minus J omega C V RMS squared equals minus J 21.07. Let me write it in VARs. So it's 210770 VARs. Right? I just need now to, I want to find what kind of capacitance is required. So I just do the math now. J minus J cancels with minus J. I end up with C being 21070 over omega, which is 2 pi 60, and then 220 squared. If I do this calculation, this turns out to be 1154.7 microfarads. Or if I represent it in millifarads, this is going to be 1.155 millifarads. This is the value of the required capacitance. Okay. All right, so that's it for this chapter. I'm gonna assign after this a bunch of homework problems. There are like two more sections, which are the sections about safety, considerations, and single phase three-wire circuits, right? And those are mostly topics with that relate to power systems. I will skip them for this course because they are not incredibly relevant for a circuits course. But I suggest you read through these sections anyway for your for your education. I won't test you about them or ask you any questions about them in exams, but I highly recommend you just read through those sections. They're very informative. All right. So I think the next we're going to start with the next chapter. See if we have time today, but yeah, that's it for power analysis in AC circuits. Let's start our discussion of magnetically coupled networks. And we want to start by introducing the concept of mutual inductance. And to introduce this concept, we want to go back to the. So if you remember in circuits 1, you started studying the physics of inductors, and that led you to the circuit relationship for inductors, the VI relationship for inductors, which turns out to be like this: VL equals L di by dt. Right, and this was based on studying the basic physical principles of inductance that guided us to this equation. In circuits, we only care about this equation. We don't care about the physics, right? Because we are lumping everything. We are just only concerned with V and I and the relationship between them for every element. We don't really care about the underlying physics too much, other than allowing us to guide us towards getting those lumped equations that relate V to I, right? That's all what we care about in circuits, relating V to I and solving circuits, right? And this relationship varies between resistors, inductors, and capacitors. So those are the three basic passive elements that we studied so far, right? In terms of conductance, there is now an extra concept we want to introduce, which is what's called mutual inductance. Up to this point, when you are talking about inductance, what you mean is self-inductance. Right? That's the inductance that you mean when you talk about pure inductance, right? But due to physical principles, there are other kinds of inductance that we will bring up in this chapter, and they are important concepts because they lead us to the underlying principle for the operation of the transformer. Transformer is a device that is based on mutual inductance that allows you to take in a voltage and apply a gain to that voltage so that you get a much higher voltage at the output of the transformer. So the transformer is a very important device, and to understand the transformer, you need to understand the concept of mutual inductance. All right. So what are the basic principles that allows us to derive the relationship between the voltage of the inductor and the current of the inductor? Well, the two underlying physical principles are Ampere's law and Faraday's law. Ampere's law, we won't write it down in detail, but all it amounts to is that if you have any current flowing in a conductor, this current is going to generate a magnetic field. Right? There's going to be a magnetic field in space around that conductor. And Faraday's law states that, of course, this field is going to generate a flux. A flux is just a magnetic field multiplied by an area, cross-sectional area. Right? So B times A is just the flux. So it has units of Weber. You just have units of Weber because magnetic flux density B has units of Weber per meter squared. Okay. Faraday's law states that the rate of change of the flux gives me a voltage. If I have a circuit, let's say I have some magnetic flux, some magnetic field that is changing with time, right? Then if I have a circuit, let's say I have a closed circuit around that flux, this changing flux is going to cause a voltage to appear on the circuit. So I'm going to see a voltage here appearing on the circuit due to this changing flux. Right? So Ampere's law and Faraday's law, those are the two basic laws that allow us to derive the properties for inductors. So let's review that a bit. Let's review. I know you did that last semester, but let's review it. Review the physics of inductors, right? And let's draw an inductor as a coil. So I have a wire, when I have a certain coil like this, and I have, let's say, n turns. Okay. So when I have a current, let's say I1 here, passing through this coil, this generates a magnetic flux, right? So there's using the right-hand rule from physics, the current is passing this way, and using the right-hand rule, it's flowing counterclockwise. Using the right-hand rule, that tells me that the magnetic field is going up like this. Okay, and the total the field times the area, cross-sectional area of this coil is just going to give me the flux, the total magnetic flux. Okay, now this is Ampere's law. This is like a qualitative statement of Ampere's law. Without writing any equations, I can tell you the current flowing is going to generate a magnetic flux. Right. Faraday's law states that the rate of change of this flux is going to generate a voltage, but this is true, by the way. This is Faraday's law only for one loop. Here we have n loops, right? So each one of those loops is going to generate its own voltage, but all of those loops are connected in series, right? Because they are connected in series, the voltage will be the sum of all those voltages. So really, I mean, we need to use like adjusted form of Faraday's law that accounts for the multiple windings that we have. And to use that adjusted law, we introduce the concept of flux linkage. So flux linkage is just flux times the number of windings, right? That's what flux linkage is. So this is called flux linkage, right? We introduce flux linkage because it is the rate of change of flux linkage that gives me the voltage across the coil, right? This is just a way to account for I introduce flux linkage instead of flux, just to account for the number of windings in the coil, right? So that I don't calculate the voltage for every loop and then sum them up. I just say, hey, imagine that the flux is just doubling because of n times, because we are repeating this thing n times, right? So the voltage is going to be repeated n times. So it's a different way of adding n here. So let me state it another way. So the voltage due to the one loop is d phi by dt. But because I have n loops, what happens if I have n loops in series? I just sum it up, right? Sum the voltages up to get the total voltage, and I just take the n inside. So I end up with d n phi over dt, and I just say I call n phi the flux linkage. That's where the flux linkage comes from. It's n times phi, such that when I differentiate lambda, I get the voltage, total voltage across the coil. Okay. Now, once I've derived defined the flux linkage, notice that the flux is kind of like a three-dimensional thing. It's something that's distributed in space, and it's going all around here, going out from the coil. It's in 3D space. In circuits, we always like to lump those things, kind of like similar to a resistor, right? A resistor is a chunky thing in 3D space, and the current is flowing everywhere. But we lump the current into a certain constant single variable I. We lump this whole 3D thing into one value R, right? And so on and so forth. So same thing here. We want to relate the flux linkage to I, right? I is what's generating the flux and the flux linkage. So we want to introduce a lumped parameter that just multiplies with I, and that gives me the flux linkage. So this lumping, this way of making the flux linkage only depend on I, this is what's called a lumping parameter. And this is the definition of the inductance. This is the inductance, or what we call the self-inductance. Okay, we know from Faraday's law now that V across the coil. This is V equals d lambda by dt. Right? This is Faraday's law. And so I plug this in and I end up with my familial equation, V equals L di by dt. Okay. So this is a quick review of the physics of a self-inductance, of a single inductor. Where does this formula come from? Okay, it comes from Ampere's law and Faraday's law. Ampere's law states that I get a flux from a current. Instead of dealing with the flux, I deal with the flux linkage, because it's according to Faraday's law, it's the rate of change of the flux linkage that gives rise to the voltage. I lump the flux linkage so that I can make it proportional directly to the current. I find the constant of proportionality with respect to the current, which is a lumped parameter, and this introduces the concept of inductance. And I then apply Faraday's law to get the VI relationship for an inductor, right? And then after you do that, you did that in circuits 1, you forget this whole thing. And because we're doing circuits, we're not doing physics, we only focus on this equation, and that's what we use to do circuit analysis and to solve problems and so on and so forth. Okay, so the physics was guidance for us to reach this equation. But once we reach this equation, we run with it, right? Now we want to kind of like do the same thing. We want to start with the physical concepts, and we want to use it to guide us towards the concept of mutual inductance. But once we reach this concept, we're going to forget about this and just use the equations that we get for mutual inductance. So this is the guiding philosophy here. All right. So what's the idea of mutual inductance? The idea is that we have this coil. Let me draw the circuit again. I1. And then we have this coil. So this coil is going, this is I1. This coil is going counterclockwise. It's rotating this way. According to Ampere's law, this should generate a magnetic flux, phi. But the idea now is that there is a coil adjacent to it. Right? And this coil that's adjacent to it is this flux here is going to pass through that adjacent coil. Right? That's the idea. Is that mutual inductance happens because the magnetic field emanating from a coil is distributed everywhere in space, right? And typically, if there's another circuit, another coil that's far away, the effect will be small because that field is going to dwindle as it reaches the other coil or the other circuit. But if the other coil is close enough, the magnetic flux is going to affect the other coil, and there's going to be like a mutual effect between them. This circuit 1 is going to affect circuit 2, and circuit 2 is going to affect circuit 1. We want to quantize that. We want to express that in an equation. Okay. The key thing here is that the flux is shared between the two coils. So let's assume the other circuit is just open from that side, and there is V2. Right. So now we have circuit 1 and circuit 2. Okay, so and we have coil 1 and coil 2. Coil 1, let's say it has N1 turns, coil 2 has N2 turns. Right? So what is the flux linkage for coil 1? It's just N1 phi, and we said we lump this with using L1 I1. L1 is the self-inductance for coil 1. That's what it is. Okay, and we said V1 according to Faraday's law is just d lambda 1 over dt, which is L1 di1 over dt, right? There is no current in circuit 2 because it's open at this point. Okay, So this is L1 called self-inductance. Okay, what about circuit 2? What would be the voltage that arises on those terminals, right? Well, same thing, we need to find the flux linkage for coil 2. Flux linkage for coil 2 is just N2 phi. The key thing is that it is the same phi. The flux that is shared between the two coils is the same. I just have to apply Faraday's law, V2 equals N lambda 2 over dt equals N2 d phi by dt. Because phi is the same, notice here, I can write right? So I can write here phi, let me write this. So using this equation, I can write phi as what? Phi, I can write it in terms of I1, right? Phi is just L1 over N1 I1 using this equation, right? And phi is the same between two coils. Because phi is the same between two coils, I can come and plug it in here. So I end up with some other inductance for the second coil. I'll end up with an inductance like this. I'll end up with, let me plug that in. So I end up with N2 over N1, L1, okay, di1 by dt. Notice here that there's a voltage in the secondary circuit due to a current in the first circuit. This constant here is what we call the mutual inductance. So this is L21. This is the and this is the mutual inductance, and this is giving me the voltage in circuit 2 due to the current in circuit 1. So this is called the mutual inductance from 1 to 2, right? So you take it and you multiply it by the rate of change of the current in circuit 1, and it gives you a voltage in circuit 2. So you have an effect on circuit 2, a voltage on circuit 2 that is due to a current in circuit 1. That's why we call it mutual. While in the self-inductance case, we have a voltage across coil 1 due to a current in coil 1. So that's self-inductance. Mutual inductance is a voltage on coil 2 due to a current in coil 1. Okay. So yeah, so this is L21 is the mutual inductance. It relates a current in one circuit to a voltage in another circuit. We could also imagine L12 where we relate the current in circuit 2 to the voltage in circuit 1, right? And then we will derive all of this in general next time, but yeah, so this is the introduction to the concept of mutual inductance. I think we're out of time, so let me continue this next time. Thank you.